Okay. Right. Welcome everyone to Module 7. And so I'm going to talk now about saturation, underexposure, bit depth, and image display. So we have spoken already about saturation. You have checked in your images if you had it, or you have produced new images that should not have saturation. But now I'm going to also explain why. What's the problem with saturation? So here is an image where we have here the overlay in color, and then we have 3 channels. And at first glance, one could think that there's a problem with these 2 channels because they're very dim, whereas this one is fine because it's okay, we can see. But that is only if we just look at believe our eyes and we don't believe the numbers. Really, if we put the saturation mask on, what we can see as the problem is in this channel and not in the other 2, even though they are dim and they should be brighter. Here we have saturation, so everything that is red. So if I put my mouse above one of the pixels that are color-coded in red, I can see in here on this Nikon software, but you will see it anywhere else in your software. You can, if you hover your mouse over the image, you will see somewhere these numbers, and these are the coordinates of the mouse inside the image. And then we have the intensity of the 3 channels, channel 1, 2, and 3. So what we can see in here is that the green channel, which is this one, channel 2, has the value 4095. And even if I go to any of these red pixels, the saturated pixels, the value is the same. So this is the XY coordinate, and this is the values for each of the channels. So 4095 in all the red pixels. Of course, it's very, 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 very highly unlikely, not to say impossible, that all these pixels have the same intensity in the sample. So what does saturation look like? This is an enlarged image of this. All the pixels in red have the same intensity, 4095. If we remove the color mask, it's a little bit harder to see, but it is possible once you have a trained eye to realize that all these pixels are like a big white. There's no detail at all. So all these areas look solid white in the black and white image. There is no detail, and so this is an artifact called saturation. So what does saturation look like if we have a bead, a fluorescent bead, that is well exposed, and we draw a line in the middle and we look at the intensity profile? What we can see is that this is outside of the bead, outside of the bead. Here we go inside the bead, we have the edge of the bead. And you can see that because it's fluorescence and it's microscopy, the edge, even though the edge in our sample is very sharp, we have just outside the bead, inside the bead, it's very clear. But in microscopy, because we lose contrast, we have a softer edge. And we look at the top here, well, we can see it's all jagged. So there is definitely like some sort of texture in the image. You can see differences from one pixel to another in this image that is well exposed. However, in a saturated pixel, if we draw the same line, what we can see is a flat top in here. And so the details here are simply not recorded. And all the red pixels have the maximum possible intensity. The intensity information in recorded for the saturated pixel is incorrect. Okay, it's the wrong information, and we have 0 details. So what we need to do is basically lower the amount of photons that go to the detector because we are saturating it. So we need to lower the exposure time, lower the gain, or lower the illumination power, for example. And you need to be specifically careful when you do a Z stack, because if you set everything for one Z, you might actually have a higher intensity at a different Z, and anyway, you end up with saturation. So somehow in a Z stack, you need to do a quick check through the Z to try to find the brightest area in the sample in XYZ, and then you set your stuff for that, or you're a little bit conservative, let's say, and you don't go close to the maximum when you set. And it's the same thing during time lapses, because the fluorescence may increase over time if you have that type of experiment. So what about underexposure? What does it look like? So if we color code also the pixels that have an intensity 0 in blue, and we see something like this, there's a solid background in blue, that is not a good sign. So if we remove the color mask, it is much harder to see underexposure without the color mask than it is easy to see saturation. So it's here it's pretty much impossible to actually detect that we have underexposure without the color mask. So please do not believe your eyes and look at the numbers. If you hover your mouse here, you will see 0, 0, 0 everywhere. So this is an artifact, and the blue pixels are underexposed. So yes, it gives a very nice black background, but there are no intensity details at all at the edges of the cells. They were eaten up, let's say. They were not recorded. So it's much easier to detect saturation than underexposure. So please have this sort of color mask on. Unfortunately, this image is very, very likely to be rejected when you submit it for publication. So this is something you must be aware of because it looks pleasing to the eyes when you're by the microscope or when you're presenting it to your lab, but you will really feel sorry if the image is rejected and you have to go back to the microscope maybe a year afterwards and have to re-prepare your sample. So just do not do that. Um, So where does that come from? We have something called dynamic range and bit depth. So let's have a quick look at that. And then afterwards, we will also look at how to detect saturation and underexposure in images. You know that we can put a mask, but what is that? It's lookup tables, it's called, and we'll have a look also at histograms. So how to explore our image with the tools that we have on the microscope or in the software. And then what are the consequences of saturation and underexposure? And also how to change the display. So we'll talk about brightness, contrast, and gamma, which I spoke about before. I think brightness and contrast you have already used, but maybe many of you have not used the gamma. It's a very useful tool. So let's start with the first thing. Where does the saturation come from? Let's have a look at the dynamic range and the bit depth. So here at the bottom of the image, and again, you have this somewhere in your software, regardless of the company, I see 3 times 12 bits. And that means each of these 3 images is in 12 bits. So the detectors are acquiring in 12 bits. What does that mean? I remind you about this thing about good sensors. We get the photons. Some of them are actually detected by the detector or the sensor, and that is transformed into electrons, which are amplified. And then the voltage is read, and then it's converted to a digital signal, which is used to form the image. And this is true for detectors and cameras. So in here, in this step of reading the voltage and converting to a digital signal, we have two specifications. One of them is for this analog to digital converter, which does the conversion, and that is the dynamic range. So specification of this converter, and the bit depth is a specification of the image. So it's 2 different things. Let's have a look at the dynamic range of the sensor. This is a ratio between the highest and the lowest signal that the sensor can detect. So it's a specification of the sensor. This is when you buy a sensor, a camera, or a detector, you can have a look at these and choose accordingly. If you need, if you know that your experiments need a high dynamic range or not, you can decide what you want. But once you have the sensor, you can't do anything because this is the specification of the sensor. The ability of the sensor to read dark areas with details, okay? So fine details in the lower range of the intensity range, and also fine details in very bright areas, so as bright as possible. So we would like to have details at the bottom side of what the sensor can detect and details at the top side, and we want the top to be as high as possible. So this is the dynamic range, is the ratio between these two. So it's the specification of the sensor. You cannot choose it in the software, for example, but it depends on a number of things that you can choose in the software, like, for example, the bit depth and the readout rate. So we will have a look. But it cannot be changed after acquisition. So on camera-based systems, you know that cameras have a high quantum efficiency. And I remind you that the quantum efficiency is the percentage of these photons that are coming to the sensor and that trigger an electron. So if we have 100 photons coming towards the sensor and only 30 are detected, then we have a 30% quantum efficiency. And cameras have a very high quantum efficiency, some of them up to 95%. The exposure time in cameras is in milliseconds. So we'll have 10, 20, 100 milliseconds for the whole chip to be exposed. So therefore, during these milliseconds or tens of milliseconds, there's a lot of photons coming to the camera, and the camera has to accumulate the electrons inside before the chip is then read, converted and emptied. So the amplification and all that stuff that I've told you. And then the chip has to be emptied of all the electrons before we can acquire again. And so because we are exposing for a very long time, which is several milliseconds, let's say, we need to accumulate the electrons. And for that reason, we need to have the possibility to accumulate a lot of electrons. But we would like also to be able to read the bottom side. So the very dim signals, we want to read them with details, and we want to be able to accumulate a lot of electrons. So cameras in general have a very high dynamic range. For detector-based systems, so single point focals, detectors, as you know, have a low quantum efficiency. So instead of having like 80 to 95 quantum efficiencies like cameras, they have more like 35 to 45. So a lot of the electrons, a lot of the photons are simply not detected. On top of that, our signal is read dot by dot, like pixel by pixel. And therefore, the pixel dwell time is the time when the laser stays on one spot, and then the intensity is accumulated just for microseconds. And then the laser moves to the next spot and is read. So then the accumulation is in a very short time. So in general, the electrons are just read on the fly as they arrive, and there is no need to accumulate the charge as we have in cameras. Therefore, detectors usually they are fine with a low dynamic range. So that's one of the differences. So now we know that the dynamic range is the difference between the lowest and the brightest, but in cameras, we do need a high dynamic range. And what is the bit depth then? So the bit depth is a specification of the image. It's not a specification of the hardware. This is something you can choose in the software. And this is the reason why it's important you understand it, because you have a choice to make. So this is the number of intensity steps. Basically, the number of photons that come from the sample to the sensor it's a continuum. We can have any number of photons, but we have to digitalize the image. And as we digitalize the image in XY, in blocks, we also digitalize it in steps of intensities. So how many steps do we have? This is the bit depth of the image, okay? So we bin, if you want to say, the type of intensity, the number that we're getting, number of photons. So the intensity steps are between the dimmest and the brightest possible steps of intensities, which are also called gray levels in the image. So these are called gray levels as well. You can call them intensities in the image. So when you acquire an image and it's the intensity in white pixel is 3,500, it doesn't mean that we got 3,500 photons, okay? This is one of these steps. We get actually, it's not a one-to-one relationship. So this is something that can be set in the software, the bit depth, and that is something you can choose for both detectors and cameras. And it can be changed after acquisition. And the images, when you want to compare two images, they must have the same bit depth. Okay, otherwise you can't compare them. So how does it work? This is an 8-bit image. And you can see in Fiji, you will see here at the top, it's written 8-bit. Unfortunately, in Fiji, sometimes they write 16 bits when it's a 12-bit image. So you have to look in the metadata to see what is the bit depth. So this is an 8-bit image. And what does that mean? It means we have 2 to the power of 8 number of gray levels. And that means 256 possible intensity values or gray levels. And 256, we start at 0. So the last value is 255. So including 0, we have 256 total. And anything in the middle is going to have an intermediate intensity value and gray level. So this is a 16-bit image, and you can see how much smoother the gradient is, right? So we have a lot finer readout here in this type of image because we can differentiate almost white to a little bit less white, or almost like gray to a little bit darker gray. Whereas in here, we have bigger steps. So we have a much coarser readout of our intensity. And this is, so this is a 16-bit image, 2 to the power of 16, 65,536 possible gray level from 0 to this number, which is -1. Right, so computer screens can only display 8 bits, so 256 gray levels. And for that reason, in computer screens, except if you have, so when it's displayed, it's anyway displayed in 8-bit, regardless of what bit depth you have. So it's, but our human eyes anyway do not read 8 bits. We can only have, we have about 7 bits, so about 100 gray levels of intensities that we can differentiate. This is why you don't want to believe your eyes. What you want to do is look at the numbers. So the bit depths of, oops, sorry. The bit depth of the image, in here we have 3-bit depths, but actually we can get more. This is the way to calculate it and get the maximum. The minimum is 0, and then the maximum is the bit depth -1. And only 8 bits images can be read by any software. The images that have a higher bit depth, you need special software. For example, Fiji reads that. Your microscope software can read that, but PowerPoint cannot read 12-bit images. If you open one of your images that are 12-bit or 16 bits in PowerPoint, it will look completely black and you will not be able to display it properly. You need to bring it back to 8-bit before. So what are the advantages of having a high bit depth? Well, we have a lower risk for saturation because we have such a big range of intensities. We can read fine intensity details in both the bright areas and the dim areas. So we have a very fine readout. And also we have a better edge definition because of this very fine readout. It will not look like big blocks. Better edge definition to help segment crowded objects during image analysis. And the file size, because computers can only read in blocks of 8 bits, anything that is above 8-bit, like 11, 12, 14, and 16-bit images have the same file size on the computer, whereas 8-bit is half. So the applications for high bit depth, if your sample is very dim and very bright, or if the sample changes intensity over time, or even if your sample is middle bright, let's say, but you need to have a very fine readout of the intensities. You need to differentiate small, like a little bit gray to a little bit more gray, something like this, a bit darker. So in that case, why is it that anyone would want to use 8-bit? Because there are so many advantages in using a high bit depth. Well, first, you can only use 8-bit if your scientific question does not require fine intensity detail. So if you have fine intensity detail, we cannot. But in case you don't have such a scientific question, maybe using 8-bit is best. And why is that? It's first, you save space. An 8-bit, like disk space, an 8-bit image is half the size of all the other bit depth images. So you save quite a lot. If you have a lot of images, it becomes a problem to have high bit depth images. If you have a dim sample, there is no risk to saturate the sensor. So you're quite good with that as well. And if you need speed, then it's better to image with 8 bits because the detectors are going faster because there's less data to process. And so you can image much, much faster with a low bit depth. And yes, Angela.
Sorry, Sylvia, I'm a bit confused
Yeah.
because you mentioned before that the file size is the same for all the bit depths, but then with 8
Mm.
bit you save space.
No, sorry, I confused you maybe. The file size is the same for all these guys. Anything that is above 8.
Ah, okay, okay, okay.
Right? So
Yeah.
anything above 8 is basically the computer is going to make it like use the space as if it was 16. So the
Ah, okay.
computer will either store it at 8 or 16. And if it's above 8, it will store it at 16, even if it's only 11. So that's what I mean. So
Okay,
that,
thank you.
Sorry, maybe I can
mm,
follow up with another
yeah.
question as well.
Yes,
Yeah,
yes, yes.
because I also got confused now with when we have a dim sample, is it then better to image it with 8-bit or with higher bit depth?
Yeah. So if you have a dim sample, go for 8 bits. If you have because basically the highest intensity and the lowest intensity that you will have in your image, you will have anyway 256 levels of gray to describe it. Okay. It's a little bit the same thing as if you would yeah. So basically, you would have 256 gray level to describe the fine differences in intensity. But because your bottom and your top are not so high, anyway, you will be able to read the fine details. But if you have something that is middle brightness,
Hmm.
then you're going to have from here to here divided by 256. And that means you will have quite big steps in intensity. So then this is when you're losing the fine details. So
Okay, but then in the case,
there's no
yeah,
rule
sorry.
if you want to say. It really depends on how sort of
Okay,
bright your sample is and how much fine details of intensity. So again,
but
it's
then
not when I say fine
mhm.
details, sorry. When I say
No,
fine
no, no.
details, I do not mean fine details in I want to see small dots. I want to say a little bit more gray, a little bit less gray. Okay, so it's fine
Right.
details in the intensity.
Right, right. But then if we apply like a similar logic for very bright images or very bright like objects in our image, there, because I can think it both ways. One, that I would use also only 8 bits because if it's gonna be super bright, either way, I'm gonna be more on the edge of the spectrum of the whites. But if I compare it, of course, then with my full tissue, for example, that will
Mm.
have more darker areas, then I would go for like a higher bit depth, right? And I guess more like the second option is what you're looking for, right? For the full comparison of with your bright area
So
compared
why
to the
would
tissue.
you do something different in a large tissue or in a small tissue?
No, it's more like depending on what I'm looking at. If I'm just like looking at, if I consider just, for example, like a cell that is super bright, then I could apply the same thinking of saying like, oh, I will just use like a 8-bit depth because I'm just gonna be on the white-ish range. So I
So
don't
if
need like a super wide range, right?
so basically if you have a problem where you have a hard time setting your parameters because there's a tendency to saturate.
Hmm.
If you have that issue, you have to go to a higher bit depth. Okay. So that's
Okay,
one of the reasons why you would want to go to a higher bit depth. If there is a tendency for you to saturate, go to a high bit depth. Why?
okay.
Because the reason why you saturate is because you're trying to see some dim stuff that you cannot see very well. And then, so you're pushing a little bit to see the dim stuff, and then the rest is saturating. So if you want to see dim and bright in an image, you
Mhm.
have to use a higher bit depth.
Ah,
So
okay. Maybe that's what you refer to when you want to see both in the same image, like very dim and very bright at the
that's
same time
it.
on the image. Okay, okay. Sorry, I got it wrong. I got it
Because
like
it
one
is
or.
quite, I mean, it can happen that you have a bright sample and you only want to see the bright things, but it's
Yeah.
unusual, let's say. I think in most applications, you would want to see also what is happening in the slightly less bright areas. It depends on your
Yes.
application, clearly. So if you want to see bright and dim areas in a sample with details, you need to have a higher bit depth. If you have a tendency to saturate when you set your parameters, you need to go to a higher bit depth. If you want to go fast, you need to go for a lower bit depth.
Okay, perfect. Now it's clear. Thanks.
Yeah. So another thing is that if you have, so why would anyone want to use a low bit depth? The problem with high bit depth images is that they are heavier on the computer, and therefore an 8-bit depth image demands less computing power to do the analysis. And sometimes it becomes, when you have like big volumes, for example, it becomes a big problem to have the size of the file becomes a big problem for image analysis. So sometimes it is something where you're forced to using a low bit depth simply because you need to do the analysis in its manageable way. And also, clearly, the 8-bit images can be directly used in normal software. But the high bit depth images, they need to be converted first. It's just a small step, so it's not a big argument, let's say. But mostly, it is if you cannot. Again, it's always the same thing. You try to, once you know what these parameters mean, you try to minimize as much as possible. So you're going to try and minimize, go for the fastest possible imaging so that you don't spend all your PhD in front of a microscope that reliably answers your scientific question. It's going to be the same thing for this. If you can use 8-bit, use 8-bit. But if you have a problem with saturation quite often, especially if you do Z-stacks, for example, or if you have a problem that you cannot get fine details in the gray, in the dim areas, and in the bright areas, and you want a fine readout of the intensity, you need to go for a higher bit depth. And as you see, there is an enormous difference between 8-bit and 16 bits, even between 8-bit and 12 bits. There's a very big difference. So you get a very rough readout of the intensities with 8 bits. So if you're after fine details in intensity, fine differences, you need to go for a higher bit depth. If what you're comparing, for example, with your wild type and control or something like this, wild type Newton, something. So how to change the bit depth after acquiring? In Fiji, for example, you can go to image type, and there you could change the bit depth, I think. And this is something you have to do before you display. If you have a high bit depth image, you have to put it in 8-bit to be able to insert it in PowerPoint, for example. So only change the bit depth on a copy of the original. Keep the original intact, okay? This is very, very important. Always do not transform an image, the original image. You can do all sorts of stuff, but work on a copy. If you change the display, it's fine because you can reset it. But when you do something like this, once you've gone down to 8 bits, you cannot go back to 16, where you can, but you've lost the information. So the bit depth of the image can be downsized to 8 bits. Changing to a higher bit depth is never useful, as the fine details anyway were not acquired, so the data cannot be created afterwards. But it can be, but it's just an extrapolation, so you're not gaining anything when you go to a higher bit depth. So here are the specifications of a camera, the photometrics kinetics camera, which is a back illuminated CMOS, so it's one of the high-end cameras on the market. So it has 3,200 by 3,200 pixels, and I think people who use single point confocal will appreciate that it's a lot. And the pixels have 6.5 macrons as the size of each recording element. So if we look in here, we can see the bit depth. So we can choose in the software 16-bit, 8-bit, or 12-bit. And what does that mean? You can see the enormous implication that it has on the speed of imaging, right? So if we use 16-bit or 12-bit, we are much slower than if we go for 8-bit images. So very fast imaging, definitely. And this is the full frame. So again, I want to point out to single point confocal people that we are acquiring 500 images per second with so many pixels, right? So it is enormous. It's a very, very fast speed. Now, what we can see in here is the read noise. So I told you that the noise in the image comes mostly from shot noise, but it can also come from read noise, and there's also the dark noise. So here is the read noise, and you can see that it is influenced. So it looks like small differences, but it's actually very big differences. In the 8-bit image, the 8-bit image is going to be a lot noisier than the 16-bit and 12-bit images. So if you're after going fast and your sample is quite dim, this might be a problem because you have this noise that comes on top of the signal. And then what we can see in here, we have the dark current, which is the same thing as the dark noise. And we can, this is the minimum number of electrons that, so it means if you have no light coming to the camera, it anyway produces some electrons, okay? So we want this number to be as low as possible because this is clearly noise. And this is the maximum number of electrons that it's called the full well capacity. As I said, you will see this afternoon with Marie when we have the workshop with cameras where we compare two different cameras. You will see that the pixels on the camera pixels are a little bit like a bucket, and you have water falling on them, like the photons are falling on them, and the bucket is filling up. So we want to have a big bucket. If we have a big bucket, we can accumulate a lot of electrons inside before we read it and empty it before the next image. And you can see here that the bit depth has an enormous impact on the maximum. And the dynamic range that I spoke about, which is a specification of the sensor, is actually this maximum divided by the minimum. So in here, we'd have a very high dynamic range because we have a quite low dark current, but we have very high maximum number of electron that we can get. And whereas in here, we have a very low dynamic range. So we can go fast here, but first the image will be noisy, and we can very quickly saturate the camera because we have such a small dynamic range. Okay, so this is just wanted to show you the type of specifications that we get from a camera. So in this setting 16 bits, we're going to go, we can image, very, very bright, it was supposed to be, from very dim to very bright areas in the sample. We have a very high dynamic range, we have a medium speed, and we have a medium read noise. And in here, in these settings, we can go very fast, but we have a low dynamic range, high speed, and high read noise. And here, the 12-bit is a compromise where we have medium everything. Okay, so depending on your experiment, if you're buying a microscope, you have to think about this type of things. So now we spoke about the dynamic range and the bit depth. And I hope that you understand that what you can choose in the software is the bit depth, and it depends on the type of imaging that you're doing. It depends on your sample. And the type of, again, the how fine details you want to see and how fast you want to image. So now how can we detect saturation and underexposure? So we're going to look at lookup tables and histograms, which are tools for us to explore our image. So again, in our world, most sensors, cameras, and all detectors, but most cameras as well, acquire images in black and white, even though some cameras can actually acquire in color. They are less sensitive than the black and white camera. So this is why in high application, we use black and white cameras as well. So lookup tables, it's a strange name. Don't ask me where it comes from, but lookup tables, these are tools. So they are abbreviated as LUT. Some people say LUT. So they are tools to help us see the image, okay? So we can, for example, put an artificial color. So again, these images are acquired in black and white. But we can put an artificial color on it, and then we can change the brightness and contrast. You have practiced this already. And we can change we can color code the intensity, for example, or the Z level. We can use high-low, which you have used, so the saturation and underexposure mask in Fiji. So all these are lookup tables. it only changes how the computer displays the data. The data is not modified, so it's very nice. It means you can work with lookup tables on the original image, and you can reset that afterwards. It's only a display. So the saturation and underexposure lookup table is available on all microscope software. Please use it. So I think it's good to have it on all the time. And if it bothers you that the image is red, just do something about it and reduce everything so that the red disappears. And then it will not bother you anymore, but at least you will not be saturated. So in a Nikon software, it looks like this, but in your software, you will have, I think you have already done this, telling me where that is in your software. How can you can turn it on? And so the images are displayed in black and white with the saturated pixels in red. And what are the saturated pixels? Saturated pixels are the pixels that have the intensity of the max bit depth. Okay, so if you have acquired the image in 8 bits, the pixels will appear red when they have this intensity 255. If you have acquired the image in 12 bits, which is the case here, then the maximum is 4095, and this is all the pixels that have the intensity 4095 will be color-coded in red. So that depends on the bit depth. And the underexposed pixels are those that have an intensity of 0. So here are the lookup tables in Fiji. There is a nice little button here, and then you can change whatever you want. In Zen, it's called the range indicator. In Leica, it's called LUT. In Nikon, it's also called LUT. I do not think anyone has an Olympus microscope. Yes, someone has an Olympus. FV4000, I think. Does anyone know what it's called in the Olympus software? So I can add it to my list.
I use the FV4000, but I don't know what's
You don't know. Okay, so you're gonna have to tell me.
Okay.
Right? Okay, I think I have an assignment where you have to actually take a picture of the button or a screenshot of the button to show me that you know where it is. So be aware, though, that unfortunately in several software, I don't think it's a good idea, but this is the way they do it. Like, for example, in Zen and Fiji, the color code does not only show saturation and underexposure, but if you push the brightness, it will also show you the things that look saturated, even though they are not saturated. So I think it's not very good, but this is the way they have decided to do it. So always reset the brightness and contrast before you check the saturation so that you know what is actually saturated. So when shall we check for saturation and underexposure? Just always have the saturation mask on when imaging, and if it bothers you, just do something about it. So, oh, but I cannot see the channel color. Great. First, it doesn't matter because this is an artificial color anyway. The images are acquired in black and white. And then it's better to look at the images in black and white because that avoids the color bias that we have in our eyes, since we have more photoreceptors in green than in blue and red. And so where the green looks brighter. So just look at your images in black and white. And then all this blue and white in my image, oh, it prevents me from seeing what I want to see. Well, good. If the acquisition settings were correct, there would be no blue and red in the image. So good that it bothers you, and change the settings. Yeah. So leave it on and change the settings so you do not have any. So now we're going to look at the histogram. And the histogram is also a very good tool for you to check if you have correct settings. So this is the histogram in this Nikon software, but it's available in all microscope software. And what the histogram shows us is for each intensity in the image. So this is a 12-bit image. The maximum is 4095. So that way it stops here, from 0 to 4095, and it shows for each intensity how many pixels. So it's the number of pixels that have that intensity in the image. And what we can read from here in this image that has 3 colors, So this is a 12-bit image, so we have up to 4095. And when we look at the pixels that are at 0, what we can see is both the blue image and the red image have a lot of pixels of the intensity 0, whereas the green image does not have any underexposure. So these are underexposed pixels. That's not good. We want to avoid this. And then we will look on the other side. We can see this big peak here and the little dot to tell us, ouch, please be careful. That is telling us that we have a lot of pixels at the intensity 4095, and this is a lot of pixels in the green channel, but we have nothing saturated in the blue and the red channel. So in the green channel, we have saturation. This is no good. What we see in here is that the peaks, so the most in the green, in the red and the blue image, most of the pixels that we have, so the peak here, most pixels are in a really dim range of the dynamic range that we have. So they are very much on the left side. Whereas on the green image, we have a lot more, it's a lot more shifted towards the right, but we're saturated. So we can read this that way. We don't want to have our peaks very much to the left. And we don't want to have saturation and underexposure. And so we're going to set all our settings for in such a way that we fill the histogram as much as possible, but we avoid saturation and underexposure. Okay, so we try to shift this peak to the right side, but still avoiding saturation and underexposure. So we're going to see all this later today in when I will go with you through the typical workflow, how to set a single point confocal. We also have a typical workflow, how to set a camera-based system. Because we have so many different parameters, now I think you are a lot more aware of the way of the way the machine works. So you will maybe recognize the different parameters, but where do we start? And it's like so many of them, they all influence each other. So we made some sort of a workflow to guide you through this process. So now you can see that if I change my parameters here, and we'll see later what can be done, suddenly I have an image that is well exposed. So I have no pixels that have an intensity 0, no pixels that have a maximum intensity. And you can see that the image looks gray here. So there is some autofluorescence in the background in these two channels. But the peaks are shifted towards the middle, let's say, and we have avoided both saturation and underexposure. So this is a perfectly set parameter to acquire this sample. And then afterwards, we can do things to help with the image. So I will show you. So when we display all, so I want to show you here, when we were displaying all the 3 channels together in the overlay and not doing anything with the brightness and contrast. So I've reset the brightness and contrast. They are showing all the whole range of possible intensity. We only see the green because that's very bright and the other two are very dim. Now, if we do the same thing after changing, we can see the green, the red, and the blue, and we are influenced by the background. So it's difficult to see this image and going, something is wrong. My background is the dark. But this is a correctly acquired image, and then we can do something about it afterwards. So here there's no saturation at all, there's no exposure at all in the areas of interest. This is something that is important. If you have a big blob of antibody that is here, and this is not in the area of interest, it's okay if that bit is saturated. Okay, what we want is no saturation, no underexposure in the areas of interest. And even if you take this image and somehow you have to publish it, you can always say the big blob on the top left of the image is precipitate from the antibody and was not included in the analysis or something like this. It's fine. It's fine. As long as you can explain, there's no problem with having a big blob that is saturated. Just say it. Okay, so in the areas of interest, no saturation, no underexposure. So I want you to understand that the bit depth range 0 to 4095 is not does not represent the intensities in the image. It's the possible intensities in the image. So we cannot go below 0 and we cannot go higher than 4095, but it doesn't mean that we have in our image 0 or 4095. If our image is is acquired in a correct way, we should not have any 0 and we should not have any 4095, right? So the bit depth is the maximum possible intensities that can be in the image. All right, it's the whole range that is available to us, but we want to avoid the edges. So if we look again, if we want to see the histogram in Fiji, we go to Analyze Histogram. There's a shortcut here, and this comes up. And when we can have a histogram per channel, clearly, and we can see here the minimum and the maximum in the image. So this image is not good because it has a little bit of underexposed image. So we see minimum, maximum. This is the way we can read this. So now that we spoke about the lookup tables and the histogram and how it can help us explore our sample and also figure out if our parameters are correct or not, what are the consequences of saturation and underexposure? So here we are imaging one fluorescent bead with a spectral detector. So we have 32 channels. So you remember, we will talk today, I think. Yes, today, Gabby has a lecture about how to image multiple colors. So we're more about the spectral detection. When we want to image things simultaneously, we are shining on a single point confocal. We are shining several lasers at the same time, and the fluorescence light that comes from the sample is complex because it corresponds to the emission of several fluorophores. And then we split the emission light on a grid or a prism, and then we put lots of detectors there. This is one way out of many that Gabby will present to do spectral detection. So this is maybe the Zeiss way, and used to be Nikon that way. So spectral detection with 32 channels there. 32 channels means 32 detectors, okay? So it means each channel is making an image of the same bead. So clearly, all these beads should have the same size. But if you look at two different images here, so it's the same bead, but in different areas of the spectrum, you can see that this bead is bigger. So they should all have the same size, considering that it's the same bead. Well, if we apply the saturation and underexposure lookup table on, well, we can see if some of the channels are saturated. So saturated objects appear artificially larger than they actually are. So not only you're getting the wrong intensities there, but you're also getting the wrong size, okay? And on top of that, if you have objects close to each other, when they are saturated, because they are sort of artificially expanded, they also start fusing with each other. And therefore you get, if you count the objects, you will get the wrong number of objects, right? Because they fuse. So it is really important for, I would say, I do not know any application where it's okay, let's say, to make do with saturation. As I say, in the area of interest, okay? If you have something that is excluded from the analysis, that's okay. But if in the area of interest, there is no application where you actually get away with saturation. And again, this would be rejected if I would certainly reject it as a reviewer and say, please give me a non-saturated image. So keep the saturation and the lookup table on, and set the imaging parameters to have no saturation at all in the area of interest. Now let's have a look at underexposure. What are the consequences of underexposure? It's a little bit the same thing, but opposite. So if we look at this bead and we draw a line, this image is not underexposed. This one is heavily underexposed. And what you can see, so this one, if you remove the lookup tables, is going to go like very low contrasted. So our eyes love contrast. So we're going to be, oh, I love that one. I'm going to use that. No. Because you can see here that here we have a smooth edge of the bead, because of the loss of contrast in the microscope. And here we have a much sharper edge, and also the diameter of the bead is smaller for the, so this one corresponds to this image. So the edge is really clipped, and the all the data here is completely clipped. That's why you see it's at 0. So we get no details at the edges. We get the wrong size as well. So are you trying to publish? I think that this one will probably not attract any comment. You can see there's a little bit of blue in the background. That's okay. But this one is likely to be rejected. So keep the saturation and lookup table on at the whole time. Set the imaging parameters to have no underexposure in the areas of interest. And I want to point out that on modern single point confocals, I've said this one before, the offset is nowadays automatically set to have something that looks like this, a little bit of blue in the background, right? So on a single point confocal, it's let's say it's calculated in a different way and it's very reliable. So this, for this reason, you should not touch the offset, except if you have an old confocal where this is going to change a lot depending on your settings, then you must have it. And old, I don't mean very old, so about 10 years or something like this, it changed. You can, once you have those images, even if you are not happy because it has some sort of high background, which comes in this case from the mounting medium being autofluorescent, you can fix this after acquisition. So please acquire your images in the correct way. That can be fixed afterwards. But if you acquire them with saturation and underexposure, it cannot be fixed afterwards. So here we have the correct exposure, and there's no red and blue. And then what we have is that we can select here an area in the background and then subtract this. So we can acquire images without underexposure on a one-point confocal like this one. And the underexposure is not possible with cameras. So you don't need to bother with cameras because the cameras have this offset of about 100 counts, because cameras cannot deal with 0 values. So the manufacturer puts an offset, and therefore it's not possible to have underexposure with cameras, only on single point confocals and only on the older types. Then you can subtract the background this way, and this way you can remove the autofluorescence in the mounting medium, and you can also remove the camera offset. And that is done after acquisition. Clearly, any images that you want to compare, you have to treat them exactly in the same way, with the same value and the same, you do exactly the same thing. And you mention what you have done, like background removal, in the material method of your paper. So in saturation and underexposed images, the information, the intensity information recorded is definitely incorrect. And the size of the object is likely to be incorrect. And the number of objects is, if they start fusing, is likely to be incorrect as well. The correct intensity and size information cannot be recovered after acquisition, and saturated and underexposed images are likely to be rejected. That would hurt very much. Do not believe your eyes. Put the lookup table on all the time when you're imaging, and write in material methods something that shows people that you know what you're doing. For example, the imaging parameters were set to have no saturation or underexposure in the images. When the reviewer reads this, they are reassured that you know what you're doing. So I think I've said that a number of times. Yeah, so this is really important. Saturation and underexposure are artifacts of microscopy. We don't want them. Let's have a little break. And I think we take a 10 minutes break. So let's come back at 10